So good evening all of you. Today is our week 5 discussion, and if someone is new to this session, kindly I request you to please introduce yourself first. Is my voice audible, guys? Hello, is my voice audible, guys?
Yes, sir, you are audible, sir.
Okay, so I think nobody is new to this session. Everybody has introduced themselves. So let me start. So is my slide visible to all of you, guys?
Yes, sir.
Okay. So, welcome all of you to week 5 discussion. So, till now we have started our discussion with introduction to soft computing. Then we have covered some portion of fuzzy sets, fuzzy theories, and then fuzzy logic controller. And then in the previous two classes we have entered the GA, genetic algorithm. And today also our discussion will be mainly on genetic algorithm, and we will start a portion of multi-objective optimization. So I hope you all got the previous week's discussions slides and videos, right? Hello. Okay, so I am assuming you all got the previous week lecture video and discussion slides. So let me start with week 5 discussion today. Introducing myself, my name is Ayan Paul. I am PMRF Research Scholar from IIT Kharagpur, and this subject name is Introduction to Soft Computing, and this is taken by Professor Devashish Samanta, Department of Computer Science and Engineering, IIT Kharagpur. Now today's discussion. Now in the previous discussion we have discussed about crossover technique in binary coded GA, but there are other two type of GA. One is real coded GA and another one is order coded GA. So today we will be seeing crossover techniques in both this GA. So starting with crossover techniques in real coded GA. So real coded GA, there are three types of crossover mainly. We will start our crossover discussion with linear crossover. So in GA, in this real coded GA, any crossover is done by this alpha parent 1 plus beta parent 2. So crossover, you all know, two parents participate in reproduction, and then crossover happens, and this is the formula for crossover techniques in real coded GA. Now we will be seeing different crossover techniques. So first one is linear crossover. In linear crossover, two parents reproduce or take part in reproduction to form three children solution. These are the three children solution. One is 0.5 into parent 1 plus 0.5 into parent 2. Second one is 1.5 into parent 1 minus 0.5 into parent 2. And third one is minus 0.5 parent 1 plus 1.5 parent 2. And we will be as we know that in GA what we do is, if there are two parents then there will be two children, but in this linear crossover what we do is we get actually three children. So we will be taking best of the two childrens. So how we would know what are the best ones? See, if there is maximization problem, then you will take the maximum fitness children, and if there is minimization problem, then you will take the minimized fitness children. So this is your linear crossover. Now linear crossover, let's see within let me erase this. Okay, so linear crossover, let's see with an example. So there are two parents, P1 with 15.65 and parent 2 18.83, and we have to do linear crossover to get the children solutions. So children solution, as I have already told, these are the three children solution that will be forming. One is 0.5, excuse me, there is someone. Okay. Yeah. So so parents are 15.65 and 18.83, and so first children will get by this formula 0.5 PR1 plus PR2 or P1 plus P2. So 0.5, if you will do 0.5 P1 plus P2, you will be getting 17.24. Similarly, C2, how you will get C2? C2 you will get by 1.5 parent 1 minus 0.5 parent 2. So this you will do the calculation, you will get 14.06. And third, minus 0.5 PR1 plus 1.5 PR2. So minus 0.5 P1 plus 1.5 P2 you will do, and you will be getting 20.24. So for this two parents, 15.65 and 18.83, this are very your two parents, and we are getting three children solution. One is this C2, C1 and C3. And if our problem is maximization, then we will be cutting this solution, because this we don't need, because we are doing maximization. So we will be selecting this two of the best solution. So our solution would be for this parents 15.65 and 18.83, our children solution would be 17.24 and 20.42. Okay, so is this part clear to all of you guys? Hello. Okay, so I think this is the most simple thing. There is a formula, and by the formula you can get direct answer. Nothing to worry about. Only take care that you will get three children, and you have to eliminate one children to have the two children. So you will be eliminating one children, and you will keep two best children in the solution. Okay. So our next type of crossover is blend crossover. So blend crossover, again two parents will be participating in crossover, and you will get again two children, and this time children you will be getting by this formula: 1 minus gamma pr1 plus gamma pr2, and another children 1 minus gamma pr2 plus gamma pr1. So how you will find the gamma will be found out by this equation. Gamma equals to 1 plus 2 alpha into r minus alpha. Now alpha will be given to you as well as r will be given to you. Also note that the value of both alpha and r will be in between 0 to 1. R you will take 0 to 1, and alpha, it is a fixed value, also you will take 0. You will take any value, means between 0 to 1. So normally what we do is we take alpha as 0.5, but if it is given in question some other value between 0 to 1, you have to take that. So let's again see the example of this two. Again same parents, 15.65 and 18.83. And here already your gamma is given, so no need to calculate gamma. If gamma is not given, then you put this formula and calculate gamma, but gamma is already given, that is 0.6. And when you will calculate, you will get two children solution. One you can calculate with this two formulas, and so here we are getting two children solution, 16.60 and 17.88. So I think this is also clear. Again I am repeating here this is the formula for the two children. One is 1 minus gamma pr1 plus gamma pr2. Second is 1 minus gamma pr2 plus gamma pr1, and gamma is calculated by this formula: 1 plus 2 alpha into r minus alpha, and alpha value you can take from between 0 to 1, but normally it is taken 0.5, and r you can again take from any value from 0 to 1, and you will be getting this answer here. As gamma value is already here as gamma value is already given, that is 0.6, so you can find the children solution by directly putting the gamma value in this formulas. Is this also clear to all of you? Is this clear? Okay. So I am again telling, guys, you please be interactive with me, otherwise I won't be getting where exactly you are facing difficulties. So you can openly tell me that this portion is not clear or this part is not clear. So more the interactive will be class, more we will learn together. Okay. So I hope you please interact, and you can interact by unmuting yourself, or you can write in chats. Okay. Okay, so let's move to the next question. So we have done with two crossover, linear crossover and blend crossover. Now we have the third type of crossover called simulated binary crossover. And in simulated binary crossover we find a factor called spread factor, and this spread factor is alpha equals to children 1 minus children 2 by parent 1 minus parent 2. And what is the significance of the spread factor? This spread factor tells what is your kind of crossover. So then generally there are three type of crossover. One is contracting crossover, second is expanding crossover, and third is stationary crossover. So let your parent solution is lying between, this is your P1, Why is this name blend? Okay, blend crossover. So this name, I exactly don't know why is this called blend crossover, but I think as it has to do with some weights. Actually, if gamma, you are blending this two, parent one and parent two, and with equal weight. Like if you are given this W1 gamma, if you are telling W1 and like P1 for parent one, W1 P1 plus, actually what you are doing is you are doing 1 minus the weight, right? So actually you are blending here, you are blending with some proportion, you are giving some proportion to this parent one, and you are giving next proportion to parent two. Similarly, in children, what two, what you will do is you just exchange this, you do WP2 and 1 minus WP1, right? So you are kind of blending two panels to get the children solution. So I think this is only the meaning of blend crossover. More you can learn in detail, but this is, I think, only the name for this blend crossover. Okay, Murugesan? Hello?
Okay, sir. Yes, sir. Okay.
Okay. So yeah, I am discussing the third thing, that is simulated binary crossover. So Murugesan, you can unmute yourself. Okay. So yeah, you can mute yourself. Okay, you are muted. Okay. So yeah, the simulated binary crossover. There are this spread factor, significance of spread factor, right? So there are two parents, P1 and P2, and this spread factor, how we will say it is contracting, expanding, or stationary crossover. If your crossover is contracting, then your then your children's solution will lie in between parent 1 and parent 2. This is known as contracting crossover. Now if your crossover is expanding crossover, then your children will lie ahead or behind the parents. So this is your expanding crossover. So let me write it with C and E, expanding E and E. Right, so these two are contracting crossover because this crossover is coming in between two parents, and when your crossover is lying beside the two parents, that is known as expanding crossover. And third type of crossover, stationary crossover. If your crossover is stationary, then it will lie exactly in place of parent, like this will be your C1 and C2 if this is a stationary crossover. So this is the significance of spread factor. So simulated binary crossover gives this spread factor, and yeah, now how to solve this question of spread factor. Let's see the steps for solving how to get the children solution in this crossover thing. Okay, so to get the children solution, first you have to choose a random value of r, that is that will be between 0 and 1. Then what you will do, you will put this formula and determine this alpha dash, right? So what is this C alpha? C alpha is for this contracting crossover according to simulated binary crossover. This C alpha will be given by this equation. So ultimately what you do, you put this equation 0.5 q plus 1 alpha q here, and you do the you solve this definite integral, and you find alpha dash value. And when you when you got the alpha dash, your children will be 0.5 pr1 plus pr2 minus alpha dash pr1 minus pr2. Similarly, you will get children 2. Similarly, if this is expanding crossover, you have to use this formula, right? So for the expanding crossover, this r value will be greater than 0.5, and here expanding crossover ex alpha 0.5 q plus 1 1 by alpha q plus 2. So let's see this by a numerical example. It will be more clear. So these are the two parents given in this numerical example, 20.65 and 15.50. Okay, so someone is joining in. Okay, so these are the two parents given, and q equals to 3 given. This q equals to 3 is given, and you have to do the solution. So we have taken r 0.4. You can also try with expanding crossover, and you can take r r above 0.5 also. So we have actually tried this with contracting crossover. So for this contracting crossover r less than 0.5, you have to use this formula, c 0 to alpha dash c alpha d alpha equals to r. So that's what here has been done. 0 to alpha dash c alpha d alpha r, and c alpha alpha you will find by this equation 0.5 q plus 1 alpha to the power q. You do this definite integral, and when you do this you will do this definite integral. Here see 0.5, you take it out 0.5, your q is 3, right? So 0.5 into 4, you take it out, alpha to the power q, right? Alpha to the power q is alpha to the power, when you will do the integration, let's do this. Zero to alpha dash, right? Alpha to the power q d alpha, right? This will be your equal to, you have taken r as 0.4, right? So 0.5 into 4, when you will do this this integral for alpha q, that will be equal to alpha to the power 4 by 4, and your limit will be from 0 to alpha dash, and that will be equal to 0.4. And you cut this 4 with this 4, and that will be equal to 0.4 by 0.5 will be equal to 0.8, right? And that will be equal to alpha dash to the power 4. So alpha dash to the power will be coming 0.8, and when you will solve this, you will get alpha dash as 0.94, and when you are getting alpha dash, you will get this two children solution as 0.5 parent 1 plus parent 2 minus alpha dash parent 2 minus parent 1, and similarly 0.5 parent 1 plus parent 2 plus alpha dash parent 2 minus parent 1. So you will get this two solution as your children solution for this two parents, parent 1 and parent 2. And let me erase this. Okay, So how do we know our solutions are contracting one? You see, our parent were 20.65 and 15.50. So these are our parents 15.50, 20.65, and our children's solution coming 15.66 and 20.50. As this 15.66 and 20.50 is lying between 15.50 and 20.65, this is your contracting. This is your contracting solution. This is your contracting solution. So is this clear, this part? So is this part clear to all of you guys? Any doubt in this part? Okay, so no doubt, right, in this part? Okay, so let me move forward. So let's move forward. So till now what we have done crossover in real coded GA. Now there is another type of GA known as order GA. Order GA is very similar to your binary coded GA. Only in order GA, your order is very important. Like in binary GA, and that this will be anything between 0 to 1, 0, 1, anywhere. So that you can see in binary GA, these bits are repeating. But this is the difference between order GA. You will not see these bits repeating themselves. So this is known as order GA. So how to have the crossover technique in order GA, we will see. So here also we can solve it by single point crossover. And how to solve this single point crossover? See, you will find this children one solution by totally placing first you have to do this imaginary bar. Here same procedure as we have done in binary coded GA. You have to put a stationary bar after any bit, and then we have to create the children solution. So children one solution is created by exactly copying bits of parent one. So again I am telling, children one is created by exactly copying the bits of parent one up to this imaginary bar, right? So we are exactly copying. We are copying A here. We are copying C here. We are copying D here, and we are copying E here. So we are exactly copying the parent bits to this parent 1 bits to this C1 bits. Okay, and now how we will get this thing, that is what after the bar. So after the bar you search with your you search bits from your parent 2. So again I am telling, for this up to this bar you copy exactly the left of this imaginary bar to C1, and after this bar you copy from this parent 2, right? So see, as we are copying this part from this parent one, so we are exactly writing this. So A, C, D, E, we are exactly writing this. Then we are coming to parent parent 2. So how we are coming to parent 2? See, we are starting from here. So sorry, we are starting from here only. So see, as E is already there, we can't write E. Then D is already here, we can't write D. C is already here, we can't write C. but J is not here. A, C, D, E. J is not here. So we are transporting this bit to here. Then I is not there. Then we are transporting this bit to here. Similarly, H, B, A is already there. So again we are cutting. We are not transporting. F, F till now F is not there. So we are putting it here. G is not there here, so we are putting it here. So again I am telling, you put a imaginary bar, you copy exactly the bits on the left side of parent 1 to this children 1, and for right side bits of children 1 you take the bits from P2, but only on one condition, that no of the bits should be repeated. So when it is repeated we have cut here, and when it is not repeated we have transported the bits of P2 to C1. Okay, similar procedure you do for C2. So is this clear, guys? Is single point crossover clear in order GA?
Hello, sir.
Yeah.
Sir, is there any condition the choosing of the position of the k value? If you choose the k value in left, it totally change the original position. No.
No, there is no condition like that. There is no condition. You have to choose in between. Normally we choose. See, you should not choose here, because if you will choose here, then all your bits will be copied here. So the uniformity will be more. So we want something like the uniformity should not be very much, as well as the uniformity should not be very less. In between we generally choose. So here we have chosen at fourth position. So there are no rules as such, but generally what we do, we choose from third position to 6th, 7th position, that we do. But there is no rule for this, right? You can also do here, but if you will do here, all your bits will be copied here, so uniformity will be more. So our purpose to do crossover would not be fulfilled. That is why we choose somewhat in between. Okay. Hello. Okay, so I hope this is clear to all of you. Okay, so let's move to the next one. So yeah, guys are joining today. Nice. Okay. So 2-point crossover. In 2-point crossover, what we do? You remember the 2-point crossover of binary coded GA. There also we put two imaginary bars in the parents. So we have put two imaginary bar, one after the fourth bit and one after the 7th bit. Okay. So when we have put this, what we will do, like single point crossover, in between what are the bits, we copy of P1 in between this imaginary bars K1 and K2, whatever the bits, we exactly copy BFG from P1 to C1. So we have exactly copied BFG from P1 to C1. Now what about the remaining bits, that is beside the imaginary bar as well as after the imaginary bar? So for bits before and after this imaginary bar, what you do is you take the bits from P2, but only one condition, that bits should not be repeated. So here as BFG and BFG is not there, so we are keeping E, we are keeping D, because D is not in BFG, we are keeping C as D is not in BFG, and J we are also keeping, we are keeping I, we can keep, yes, I we can keep, H we can keep, yes, we can keep, B, as B is already here, so we can't keep B from here, right? Then we have to look for next bit. So next A we can keep, right? So again I am repeating what you do, you put two imaginary crossover bars. In between the bits you copy exactly of parent 1 and children 1. And for the other bits for children 1, what you do, you take the bits from P2, provided that this bit should not be repeated more than once. So that is how you do the 2-point crossover. And third is your let me erase this. Next is your position based crossover. Position based crossover is very similar to 2-point crossover. Only difference is here you are putting two imaginary bar and copying all these bits to the children bit. Here you fix some bits, or you fix some strings. So here we are fixing the third string, the fifth string, as well as the eighth string. This three strings we are fixing, and whatever strings we are fixing, we are copying exactly same bits of the fixed string to the children 1, right? So from P1 we are copying exactly the same bits that we have fixed to children 1. So here we have fixed K1, K2 and K3, that is D, B and H. So we will copy exactly this D, exactly this B, exactly this H to this children 1. And for other bits, what we will do, we will take the help of this P2, and we will copy all these bits provided that no bit should be repeated more than once. So here we are copying E, here we are not copying D, because D is already we have done. So we are cutting this D. C we can keep, J we can keep, I we can we can keep, this H is not, because H we have already copied from this P1, so we cannot keep. B we can keep, no we cannot keep, because we have copied this from P1. So again this I am cutting, this we are keeping, F and G we are keeping, right? So we are cutting this this bit and this bit, because we have copied this bit and this bit from parent 1. So that is how you will get C1. And alternatively, similar process you can do for C2. And this is the last crossover, that is called precedence preservation order crossover. Here is like your uniform crossover in binary coded GA. Here this mask is provided, like binary coded GA. You are doing this mask by tossing the coin, and if head or tail comes, you head or tail comes, you take a decision that which bit to select. So here this is your mask. So according to this mask you will select the children's solution. So here this mask is telling 2. So for this C1 you have to go to this parent 2. So E is selected. Now wherever there is E in both this panels, you cut E, all the E's. So we are cutting E here, and if there are some other E over here, no E over here, so we have cut this E. And now for second bit 1. So 1 as 1 it is indicating, so we will be selecting parent 1. So 1 is C. So we are keeping 1 is C, so we are keeping the C. So we had selected C, and other C we will cancel out, because we cannot select C after this. Similarly we will do the other bits procedure. So again I am repeating, for this precedence preservation order crossover, it is very similar to your uniform crossover in binary coded GA. As in binary coded GA uniform crossover, you had been given some mask, and according to that mask you decide whether to swap the bits or not. Here this mask is given to decide whether you should be selecting from P1 or you should be selecting from P2. So if 2 is written, then you shall select from P2. If 1 is written, then you select from P1. But only you have to take care that no bit should be repeated more than once in your children string. So this is the logic. So in this 4 crossover, any doubt you may ask. So any doubt in this 4 type of crossover? Hello, am I audible?
Sir, what is the meaning of precedence and preservation meaning?
Precedence preservation. Precedence preservation means, see, again I am explaining. Okay. Precedence preservation. Precedence preservation means if a bit has come once, it cannot be repeated again. Like here, for this 2, we have selected E bit, right, in our children's string. Now precedence preservation means this E is preserved in our children's string and it cannot be repeated from any of the 2. Like if here is another bit, right? If this is extended, if here is also E is there, if here, like here also another bit is there and this is giving 2 and your 2 is in here, like here is E, here is, let's say, Z, let's say, right? So here we cannot, our mask is telling we have to choose the E, but we cannot choose the E because E is already preserved here, right? E is already preserved in our children's string in the first bit only. So that is why we cannot use this E here. We have to look for other bit apart from this E. So that is why this name precedence preservation order crossover means if a bit is selected, it is preserved and you cannot, even if your mask is telling to go for this parent, to select a bit from parent 2, you cannot do because you already have this bit in your children's string. Okay? Is this clear?
Okay, sir. Okay.
Okay. So let's move on to the next things. So crossover scheme, till now we have done with the crossover scheme. Now similarly for binary coded GA, there are 3 mutation scheme. So one mutation scheme I have already discussed while doing the GA equation, GA long quotient in the previous discussion. Here also we will see other 2 GA mutation scheme. So one is flipping. This is the most common GA. Okay, let me here also tell you one thing. So here you have 4 crossover scheme, right? Now if in your question it is not given what type of crossover scheme you should put, so go with the most simple crossover, that is single point crossover. Similarly in mutation also, if nothing is given, like our previous GA question, in the previous discussion, the GA question we have solved, there nothing was given for mutation. So that is why we choose the most simplest mutation, that is flipping. So flipping, here you can see wherever this is your mutation probability. Mutation probability where 1 is there, you have to just flip the bits. Like in your parent, here the bit was 1 and here mutation probability was 1. So you have to flip the bit, that is you have to change 1 to 0. Similarly 0 0 0, so in this 3 bits you no need to do any changes, so it is copied 0 1 and 1, it is copied as it is. But here again the mutation probability is 1, so in this bit again you have to flip the bit, so you have to change this from 0 to 1, right? Similarly this 2 0 0, that means no mutation is taking place at this 2 position, so 0 and 1 is copied to your children's string as it is, right? But here here in this last bit 1 is given as mutation probability, so you have to flip this. You have to flip from 0 to 1. So this is flipped. So this is the most simplest technique to do the mutation in binary coded GA, that is known as flipping. So if nothing is given in your question about what scheme you have to use in mutation, you choose the flipping scheme. There are other two schemes also. One is interchanging scheme and another one is reversing scheme. So let's see what these two are telling. In this interchanging scheme, 2 bits will be given to you. Particularly 2 bits will be given to you, and what you have to do, you have to interchange this value in between 2 bits. So 0 will go to this position and 1 will go to this position, right? And here in parents you see the other are copied as it is, like 1 is copied as it is, here 1 is copied as it is, 1 copied as it is, 0 copied as it is, 0 copied 0 0 copied as it is, and yeah, here this 0 will be, this is a typo, here 0 will be 0 copied as it is. But in this in at this 2 position you have to interchange the values. So this 0 will become 1 here, and 1 is and 1 will become 0. So this is known as interchanging. And another one is reversing. Reversing, what we do, we flip the bits but alternate bits. Wherever the star mark is there at this position. So after this star mark, we reverse the position. So here not reverse the position, we flip the bit. So after this star mark, this is your position. So at this position you will be you will be reversing the bit. So 0 will be changed to 1. Others are as it is. This 1 will be copied as it is, 0 1 1 0 0. So all other bits are copied as it is. The other position after the star mark, you have to flip the bit. Okay, is this clear to all of you? Is this thing clear to all of you? Mutation scheme in binary coded GA? Any doubt? I hope this is simple actually, but any doubt at any position you might ask. Okay. So next is mutation technique in real coded GA. Now we have learned a mutation technique in binary coded GA. There are also mutation technique in real coded GA. So there are basically 2 mutation technique. One is random mutation and another one is polynomial mutation. So random mutation, how you will find the mutated bit? You will be given a original bit, and original bit, what you do, you find a but this delta is known as perturbation factor. Generally this delta will be given to you, this R value will also be given to you. You have to put this formula, that is your mutated bit will be equal to original bit plus R minus 0.5 into this delta, or maximum perturbation factor, right? So again you can see by a numerical example. This is your parent, that is 15.6, R is given 0.7 and delta is also given 2.5. So direct formula you can put, that is 15.6 plus R minus 0.5, that is 15.6 plus 0.2 into 2.5. So you will be getting this 16.1 as your answer. There is again another type of mutation. This mutation is known as polynomial mutation. This formula is also similar to previous one. only one difference. Here you have to calculate this delta or perturbation factor. And how we will calculate this perturbation factor? You choose this r value. R value is between 0 to 1, so you take a r value. If r value is less than 0.5, you apply this formula to calculate the delta value. If r value is greater than or equals 0.5, you put this formula and calculate the del value and del or perturbation factor value. And when you get this del value, your capital delta or maximum perturbation factor will already be given. So your original bit is given, you maximum perturbation factor or capital delta or this triangle sign, this is also given. This only you have to find. So if this you find by this two formulas, if you know this value delta, you will get the mutated parent value. So how let's see this with an example. So original parent, it is given 15.6, similar to here also. Here we have taken rs 0.7, right, and q is given 2 and del is given 1.2. So as r is 0.7, r is 0.7 means it is greater than 0.5, so you have to use the second formula. So second formula is 1 minus 2 into 1 minus r whole to the power 1 by q plus 1. So this formula you apply and you calculate the del value. The del value is coming 0.1565. You have the parent value, you have the del value, and you have maximum perturbation factor or capital delta value. So you have all these three values you can get with your answer, and this is your mutated parent value. So these two are very simple formula based question. So I hope this is clear to all. If not, if any part there is some confusion, you can ask. Is there any confusion in this two question? Any part you can ask. Is there any question in this too? Okay, so I hope there is no question in this two numericals. So let's move to the next thing, that is multi-objective optimization problem. So we have completed our GA part to this single objective optimization. So till now whatever we were doing, we were concerning with one objective function, one object. So till now what we were doing, we were concerned with one objective function. That means last day also what question I have solved, that is one objective function. Like we have to maximize y or maximize x, like only one objective we have. But what if our objective are more than one? That type of objective problem is known as multi-optimization problem. So here you can see there are many objectives that needs to be optimized, like fx1 also needs to be optimized, fx2 needs also to be optimized. Similarly till fxn you have to optimize this, or you have to find out the minimum or maximum value for this two. So if optimization or this n value is more than m value is more than 2 or equal to 2, that is if m greater than equal to 2, that is known as multi-objective optimization. That means the objectives that you have to optimize is more than one. That is known as multi-objective optimization, and in short form we tell it MOOP, MOOP. This is your multi-objective optimization. In any optimization problem, apart from this objective function, there are other two things. One are called constraint and another are called design variables. So constraint take care take care of take care of other equations related to this objective function, and design variables take care of this x1 x2 x3 value in the optimization problem. So apart from this objective, there are other two terms. One is constraint and then one is design variables. And again I am repeating, if your objective function is more than one, or that is objective function is greater than or equal to 2, then that type of optimization problem is known as a multi-optimization problem. So this is your difference between single optimization and multi-optimization. Whenever we are doing single optimization, we are concerned with only one function, that is, let it be f x let it be fx1. So we are only concerned with one objective function. But when this is your multi-objective optimization, here we are dealing with four optimization objective functions. One is your fx1, fx2, fx3, and another is fx4. The problem with this multi-objective optimization, here you can see that at a time not all the functions are increasing or decreasing. Like here you can see, if we focus, like if we focus till this only, right, till this part only. So here you can see this blue line or the f4 function is actually decreasing at first, or this is similar to this this gray sorry, this green function, that is f3 function. So f3 and f4 function is initially decreasing, but that is not the case with this red function, that is f1 function as well as f2 function. So so f1 and f2 function are f1 function is increasing, f2 function is not starting as of, but when it is starting it is decreasing. But this is not similar with f3 and f4. So initially f3 and f4 are decreasing, but f1 is increasing and f2 has not started. So this is the challenge we face in multi-objective optimization, that not all the not all the functions are either increasing or decreasing simultaneously. Some are either increasing, some will decrease. So we have to do a trade-off in between these two to select what should be our search space in which we will get the optimum solution. So yeah, let me show you by another example. Let this be the cost of your car, and let this be comfort. So in y-axis I have taken comfort for your car, and in x-axis I have taken cost for your car. So here this two, comfort and cost, let this be f1 and let this be f2. This f1 and f2 are actually contradicting in nature. So what will happen is, when your cost is less, so our target is you have to minimize this f1, you have to minimize this f1 and you have to maximize that, sorry, minimize this f2 and maximize F1. But at a time you will see when this F2 is minimized, that is cost is minimized, our comfort is also minimized. So that is the problem here. We want one to be maximized, one to be minimized, but at a time both are minimized. So our graph would be starting from here. Then if we will increase the cost, our comfort will increase somewhere like this. If we will further increase the cost like this, like this, so our graph would be like this. But at a point we are not satisfied, because what we want, uh, we want our cost to be less and comfort to be more. We Our optimization is going this way, but what we want something like this curve. That is, when our cost is less, we want our comfort to be more. So that is known as conflicting nature of this optimization or move problem. The objective function are actually conflicting each other. So that is again I am telling, that is known as conflicting nature of this objective functions. And how to solve this move, you can do this with your multi-objective evaluation algorithm, MOEA. That is, EA is evolutionary algorithm, that is GA. GA is also a type of evolutionary algorithm. So you can also tell this as multi-objective evolutionary algorithm. So what we do in this multi-objective evolutionary algorithm, these are our objective function. You can see more than one objective function, f1, f2 till fn. So whatever data we will get, we will quote it as higher level information. Now what we will do, we will convert this multi-objective optimization to single objective optimization, like this cost and comfort. If we put a weight for this and let it be j, and if we do like this, j equals to w f1 plus 1 minus w f2. So what we are doing here is, we are combining the two objective function, comfort and cost, by putting a weight, and this weight will be between 0 to 1. This weights will be between 0 to 1. So we are giving some weight to this f1, that is comfort, and we are giving the rest of the weight to f2, that is cost. And by doing this, by forming this z, what we are doing is, we are converting this multi-objective optimization to a single objective optimization. Now we can say we have to minimize or maximize this j. So again I am telling, what you do in MOEA approach, you take all this objective function, you give some weights to each objective function, and you convert all this objective function into a single objective function, and then you can solve this problem with a simple GA approach. So that is known as multi-objective evaluation algorithm. So here you can see, we are putting this w1, w2, w3, wn to all this objective function, and we are converting all this objective function to a single objective function, that is capital F over here. And when you are converting it to single optimization problem, you use your GA to have an optimal solution. So is this clear to all of you? Is this portion clear to all of you?
Sir, I have one question, sir.
Yes.
Sir, actually, I am using the objective function, that is in terms of square value and then absolute value. Can we add two square value and absolute value as a third objective function?
Square value. What you we don't need to square, right? If f1 is your something like f1 is your x square, so that we don't care, right? F1 is your x square or x cube, that we don't care, right? We are only multiplying a weight with your objective function. So that is what we are doing. So we no need to see if your function is a polynomial function, which degree polynomial. We don't need to have care for that, right? No
Sir,
need
in
to
this
no
case,
need
you
no need to do f1 square or f2 square. No need to do that. Only you multiply some weight to your objective function. Okay?
okay, sir. You written on equation is x equal to w into f1
Yeah.
plus 1 minus w f2.
Yeah.
Where in the f1, what
Uh,
is the f1? What is f2?
f1
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 is a different objective
yeah, f1 is your comfort, right? F2 is your cost, so your comfort could vary with some other parameter like input parameter, like f1 could vary with money or something like this. Your f1 could be something in term of money, like f1 could be x minus something. F1 should be some equation, right? Could be x minus 1, x minus 2, or x square minus 1, x square minus 2. So f1 is actually a function, like f1 will be fx or something like that. Okay?
Okay, okay.
I am not getting your question fully. If you will explain me more, I can.
Yes, sir. Yes, sir. Yes, sir. My question is, sir, what are the different objective function can we write mathematically? That is my question, sir.
Objective function you can write mathematically. Any objective function. Like
You
f1 could
written
be anything,
you
like
written
x
one
square,
cube.
x cube.
You written yes,
Yeah.
sir. X for x cube you written in for single objective function. What is the objective for multiple objective function? What is the mathematical expression for multiple objective?
Yeah, multiple objective function. This is your mathematical expression, na?
Okay. Okay, sir.
There are two objective function here, f1 and f2. You are putting weights for f1 and you are putting 1 minus weights for this f2, and you are converting this two objective optimization problem, f1 and f2, to one objective optimization problem, that is z. Okay?
Okay. Okay, okay, sir.
Okay.
But W is common.
Yeah, WR
W.
is weight.
Weight is common.
Yeah, weight is
For
not common. Weight is you have to what for weight you have to do the sigma W,
okay.
right? So if you will add this W plus 1 minus W, you will get 1. Sigma W will be equal to 1. Like if there are three objective function, f1, f2 and f3, right? So you can multiply w like 0.2 for f1, 0.3 for f2, but whenever you will multiply for f3, you have to take care that sum of all the weights should be equal to 1. So 0.2, 0.3 is already used, so 1 minus 0.2 plus 0.3, that will be equal to 0.5 for this. Okay? 0.2 f1 plus 0.3 f2 plus 0.5 f3. Okay?
Okay. Okay.
Okay. So your weights sigma w should be equal to 1. This is your logic. Okay, so let's move on to the next thing. So we will be starting our assignment question discussion. So our topic would be GA operator crossover 2, crossover 3, mutation fitness in GA, and multi-objective optimization. We have just started our multi-objective optimization, so less question over here. But in the next discussion, we will be discussing more question on this multi-objective optimization. So this is the first question. So here this is for real coded GA implementation. We have to use this linear crossover, and parent 1 is given and parent 2 is given 10 and 20. So here here it is written that alpha and beta are also given. So I have at the start of the discussion I have told you that ch children will be equal to alpha parent 1 plus beta parent 2, right? This will be your children. So you can use this formula, and here these are the 4 options given. So can we have the answer guesses? You can write in chat, everybody, by guessing the answer, then I will tell you the answer. So everybody please write your guesses in the chats, then we will be solving this question. So any guesses for this question? Yeah, Murugesh is telling A. So here we are here the question is, which of the following is not a correct parameter value or not a correct children value for this alpha and beta? Okay, so let me tell you the answer. Okay, someone is joining. Okay, so let me tell you the answer for. Okay, so for first for A option, alpha, you if you multiply 0.5 with 10, that will be equal to 5, plus 0.5 into 20, that will be equal to 10. So PC is 15. So this is actually correct. This is actually correct. We in the question it is asked that we have to find find a not correct solution, right? Not correct. Which of the following is not correct? So this is actually correct. Now let's see the second one. That is 1.5 into 10. That is 15, and minus 0.5 into 20. That is 15 minus 10 is 5. So again this is also right. So here third is alpha minus 0.5 minus 0.5 into 10 if you will do, that is minus 5, plus 1.5 into 20 if you will do, that will be equal to 30. So actually this will be equal to 30 minus 5. 30 minus 5 will be equal to 25, but it is written 35. So this is actually wrong. So as we have been asked to find the wrong answer, so this is your wrong answer, and C is your correct option. Okay, so is it clear to all of you? D is also right. Mini is telling D. See, Mini, 0.9 into 10 is 9, plus 0.1 into 20 is 2. So 9 plus 2 is 11. So this is also correct. So this C or PC is equals to 35. This is the wrong answer, and as we have been asked to find the wrong answer, so C is your wrong answer. So answer C. Okay. Okay. So let's move to the next question. Which of the following crossover technique cannot be used in case of real coded GA? So A is your binary simulated crossover, B is your shuffle crossover, C is your blend crossover, and D is your linear crossover. So anyone with the guesses? Okay, Divya is telling B. Murugan is also telling B. Any other guesses apart from B? Okay, so this is simple, as I have already discussed the technique for crossover technique for real coded GA. So we have started with linear crossover, then blend crossover, then binary simulated crossover. There is nothing called shuffle crossover for real coded GA. So this is our correct answer. So answer is B. Right? So let's move on to the third question. Among the following crossover techniques for GA, which of the method is most useful for traveling salesman problem? So one, if A is your 2 point order crossover, B is your precedence preservation order crossover, C is your edge recombination crossover, and D is your position based crossover. So anyone with this one? Any guesses for this question? Okay, Murugan is telling C. Yeah, Divya is also telling C. Okay, so yeah, see, this traveling salesman problem is solved by order GA, because traveling salesman, I have already discussed in the previous class. Traveling salesman, you are visiting each city in order, and with the condition that you are not visiting any city more than once, and also you are which city you are starting your journey, you are completing your journey on the same city. These are some of the characteristics of traveling salesman problem. So this traveling salesman problem is solved by order GA, and for order GA we have seen 2 point order crossover as well as precedence preservation crossover. We have not discussed C and D, that is position based crossover. There is nothing called position based crossover for this order GA. We have not discussed this C, and the right answer is C, H recombination GA. See, H recombination GA. What you do is you like there are three cities: A, B, C, and these are given in some order. A, then B to C. So what you will do to find the children's solution? What you will do? You form a big table and you you lock one bit, like A you lock, and you find the position, like A is connected to second bit, so A2, B is connected to second bit, and you do the calculation. More detail you can see in your lecture note for more detail. Actually this is a big question, that is why I have not discussed over here, because it will take more time. So my point is H recombination GA is the perfect crossover scheme for this traveling salesman problem, as here we are concerned with this position of cities. So we have to look like which city is connected to which city is totally connected to which city. Other GA like 2 point crossover or precedence crossover, we are actually not getting this arrow marks, right? We don't know from which bit we have to go to which bit. So for this problem we will solve by edge recombination order GA. So this is the thing. So this is the fourth question. Two parent chromosomes in order GA encoding scheme is given as follows. So these are the two parents. This is your P1 and this is your P2, and you are told here fourth K point, that is some bar is given after, imaginary bar is given after fourth position, and here you are asked over here which of the following offspring is not possible. So four options are given, so you have to find out which of the following offspring is not possible. So anyone with the guesses? So guess for this question. Hello, am I audible, guys? audible?
Yes, sir. Yes, sir. Yes, sir.
Okay, so everyone kindly solve this one and have guesses for this. So any guesses for this question? Okay, so let me told you the answer. No guesses for this. So there are two parents, this parent one and parent two. So we have to do this with single point crossover scheme for this order GA, and we know what we do in single point crossover scheme. We copy the bits as it is. So where there is 1 2 3 and 4, this is actually your children's solution, because the bits are copied from P1 to as it is. Similarly, the 10987, so where there is 10987, this bit is also copied as it is from your parents to the children. So this A and C are the correct A and C are the correct answer. Now what about B and D? Now see, B and D. B is 7 8 9 10. So 7 8 9 10, like I have told you in single point crossover is you copy the bits as it is. The bits that are before your imaginary bar, you copy as it is, but you can also copy the bits before the imaginary bar in the reverse order also. So in this B, 7 8 9 10, so this is written in reverse order, so this is also correct option. So we are left with D 5 6 7 8. You can check these two parents. There is either in ascending order or descending order. There are no no children with this. There are no parents with bits 5 6 7 8 in order. So here you can see bits 1 2 3 4 or 4 2 3 1. So that is not the case in here. Here also you can see 10 9 8 7 or 7 8 9 10. That is also not the case over here. So this is not your children's solution, and we are asked which of the following is not a children's solution. So D is your correct answer. Okay, so is this clear to all of you? Okay, so let's move to the next question. Suppose the precedence preservation order crossover. So here we are asked precedence preservation order crossover, and we are given with two parents, P1 and P2, and also we are given with a mask, that is V1. So any guesses for this? Here it is asked that which one is a valid child chromosome that can be obtained from P1 and P2. So any answer? Any guesses? What is the child? These are the two parents, and we are given a mask over here. So how? Yes, Mini is telling B. Okay, Divya is telling D. Any other guesses for this? Okay, so let's see. So according to our mask, it is given 2. So out of this, what we will select? We will select this bit, that is E. So our answer could be between B and D. Okay. Now second, as we are selecting E, so other E we will be cutting. Other E, any other E over here? No. So E we have selected, and other E we had cut. Now 1 is D. D will select, other D. Sorry. Okay, 1 means the parent one, right? So C we will select. And other things we will other C we will cut. So we are cutting this C and other C. Any other C over here? No. So E, then C. So E and C. So this, I think, your correct answer. So let's B is your correct answer. E, C. So as you can see, 2 is given, so E over the first bit, and 1 is given, so we will be selecting from parent 1. So C will be your correct bit. So E, C. Now second, third. V is given 1. 1 we can select D, because D we have not selected, so D. We will be cutting D. Any other D over here? No D over here. So our first three bits are E, C and D. So our answer is B. You can check with other bits also, like here, like 2. Here 2 is 2, so we can select 2, right? 2, 1, 2, 2, yeah, 2. J. So we will be selecting J. Other J we are cutting. So E, C, D, J. Similarly, the rest of this you can check. Okay. So is this clear? Again, I am repeating. We have to follow the instruction of the mask. So our mask is telling for this first bit we have to second from 2, that is second parent. So second parent we have selected E, other E we have just cut. Then second is telling 1, so we have to select from first parent, that is we have selected C. Third is telling 1, so again we have selected D. And fourth is 2, that is we have to select from second parent, that is we have selected J. So is this clear to all of you? Okay, so I think this is clear, and yeah, B is your right answer. Okay. So let's move on to the sixth question. Which of the following statement is wrong about mutation procedure in binary coded GA? So these are the fourth thing that is given. A is a random variable called mutation probability is used to find out which bits to be mutated. B is the mutation probability is generally kept a large value to provide a large deviation. C is mutation probability is kept generally kept to a small value to provide a small deviation, and D is the offspring and the mutated offspring chromosome are of the same length. So any guesses for this? Which of the statement is wrong? We have to identify the wrong statement out of all this four one for mutation procedure in binary coded GA. So any guesses for this? Okay, Murugan is telling C. Any other guesses apart from C? Okay, so let me tell you the answer. So let's read the first. A random variable called mutation probability is used to find out which bits to be mutated. So this is true. I have also previously told you about this mutation probability, and according to mutation probability we multiply this mutation probability with our length of the chromosome and how much it is coming, like if it will come 1, 2 or 0.1, we will decide according to this how much bits we are going to bits we are going to mutate. So this is correct. So B, the mutation probability is generally kept to a large value to provide large deviation. So this is actually incorrect, because last class also I told the mutation probability is kept very less value. Like in previous class we have mutated 1 out of 36 bits. So we have in previous question, if you will see the slides there, you remember we have 36 bits, but what we have done, we have mutated only 1 bit. So that is why so we have done this because GA tells us that mutation we have to keep as less as possible. So so B is wrong answer. C, the mutation probability is generally kept a small value. This is true. And D is offspring of the mutated chromosome are of the same length. So till now we have all seen for our for our binary coded GA. Like let me show you this. Yeah, see, all this mutation scheme. Here you all this mutation scheme in this mutated offspring, you can see the length are same, like 1 2 3 4 5 6 7 8. Here also there are 8 bits, and also in the mutated there, here also you can count, here also there are 8 bits. Similarly here also you can see 4 and 4, here also there are 8 bits, and here also there are 8 bits. Similar here also you have 8 bits, here also we have 8 bits. So point is, we are not changing the length of the chromosome. Length of the chromosome is kept equal. So this is also a correct statement. So your wrong statement was B. So B is your correct answer. So also in theory you can read that mutation probability is generally kept between 0.1 by L to 1.0 by L. So if L is like 36, so you can do 0.1 by 36. To 1 by 36. So mutation probability, if you want to choose a mutation probability for your GSK, you choose a value 0.1 by L to 1 by L. Okay, so is this clear, this question? Is this question clear to all of you? Am I audible?
Yes sir, clear sir.
Okay. So let's go to the next question. Here a gene value of chromosome is given. This is your chromosome, and what you have to do, reverse mutation. So these are your 4 options. A is 0 1 1 0 1 1 0, B is 1 0 0 1 0 1 0, C is 1 0 0 1 1 0 1, and D is 0 1 1 0 0 1 1. So reverse mutation, anyone who wants to have a guess for this one? This is your parent, and you have to do a reverse. Yeah, Murugan is telling A, Divya is also telling A. Any other guesses? Okay, so let me tell you the answer. What we do in reverse mutation is, we flip the bit value for our next bit. So after this star mark bit, we have this bit. So what we will do, we will be changing this 0 value to 1 value. So our answer would be 0 1 1 0 1 1 0. So 0 1 1 0 1 1 0. So 0 1 1 0 1 1 0. So yeah, answer A is your correct answer. So this is the thing. In reverse mutation, the bit next to your random position is changed. Okay, any doubt for this question? Okay, I hope no doubt for this question. This is simple. Again I am telling what you have to do. The bit after the star mark is done at your 4th bit. So you have to focus on the bit next to your star mark. That is, you have to focus on the next bit, that is 5th bit. So in 5th bit, what you do, you flip the value. So in the 5th bit, this 0 will be changed to 1. Otherwise all the other bits, it will be remain as it is. So your answer will be A. Okay. So this is your 8th question. Which of the following is not a convergence criteria? A is a fixed number of generation is executed. B is a user defined maximum computation time is reached. C is a solution is found that satisfy the objective criteria. and D is when any individual possible solution of the population gets duplicated. So any guesses for this question? So any guesses for this question? Okay, Murugan is telling no idea. Any guesses other than this? Okay, so if you have no idea, let me give you the idea. So see, this is asks for convergence criteria for GA, and GA is converged if you reach a maximum number of generation. Last day when I given you the graph, there it was written something G max. Right, I have shown you a flow chart in the theory. You can get the slide and you can see there's a thing written called G max, and whenever your GA is going after this G max, we are converging our process. That means we are ending our process after this maximum number of generation, or G max. So this is actually correct option. See, B is a user defined maximum computation time is reached. Yes. Apart from this GMX, what you can do you can have a T max. You can have a computer program, and you can tell your computer program to end this process after a particular time. So this is also true. Answer C, a solution is found that satisfy objective criteria. Definitely, if you found your objective criteria, that is, if you found if you have to maximize, like you have to maximize f1 function, right, and you found your desired value, so definitely your GA will terminate. So this is also true statement. But answer D, when any individual possible solution of the population get repeated, like your solution get repeated, one fitness value it was coming 45, another one is also coming 45, but you have to find maximum GA, maximum fitness value, like you have to, your maximum fitness value is actually 80. So definitely if again a 45 came, your GA will not terminate, because it has to reach this 80 value. So this is actually the wrong statement out of the following. So this is not convergence criteria for GA. So answer is D. So again I am telling for this last option, here it is written, when any individual possible solution of population get duplicated. Definitely if your population is duplicated, like your population is coming 45 and again it is coming 45, these two are same, but you cannot terminate your GA, because maybe your maximum value will be 80. So if you are terminating at 45, as it is only repeating, so you won't be able to reach this maximum value, that is 80. So definitely this is not a convergence criteria for your GA. So answer D is correct. Any doubt over this question?
Sir, one doubt, sir.
Yes.
Sir, the user can design the computation time, sir?
Yeah.
Sir, that is the optimizations may take some time. If I set the computation time is 1 second, how it is possible to get the optimized value?
No, it is not possible to get the optimized value if you will set 1 second, but you can terminate your GA, right? What is the convergence criteria is given, so your GA will be terminated. Yes, you will not get the optimized value in 1 second, but your GA will be terminated. Okay, so
sir,
this
terminator and convergent, it is the same word?
Yes. Okay,
okay, sir.
so actually, yeah, you have to take some time, and then only your GA will optimize your values. But if you are selecting a very less time, like 1 second, so your GA will be terminated, right? Your GA will give you some value that might not be the optimized value, that is true, but your GA will give you some value. So this is the point. Okay. Okay, so let's move on to the next question. Which of the following statement is generally wrong about the fitness value? Fitness values appearing after a few iteration of GA. So these are the four options are given. If the fitness value are too far apart, then several copies of the good iteration are being selected while ignoring many other worst individual. B is if the fitness values are too apart, then the large amount of search space may not be explored in the future iteration. C is if the fitness value are too close to each other, then GA tends to select one copy of each individual. D is if the fitness value are too close to each other, then GA will tend to successfully capture the small fitness variation. So any guesses for this? Okay, so no guesses. So so here see, if fitness value are too close to each other, then GA will not be guided by small fitness variations, and consequently search space will reduce. So here what happens? Yeah, here what happens is here here it is asked which one is the wrong statement. Now if fitness value are too close to each other, GA follows two things. One is population diversity, and the one is selection. So population diversity will be maintained if GA if GA will not be guided by small fitness variation, means your variation should be more, then only your GA will give you good result, because it will search the entire space. If your variation is only in a particular search space like this, and your search space is originally like this, so you are here lacking the variability. So that is why this D is the correct answer. Sorry, this D is the wrong statement, and here we have asked to find the wrong statement. So this D is the right answer over here. Okay. Okay, so let's move on to the next question. Which of the following is not a fitness scaling approach? Okay, so previous question is also regarding scaling, and this question is also regarding scaling. So what happens is when you are finding the fitness value, this fitness value can actually go beyond your search space. Okay, so for this we have some fitness scaling approach. More detail you can learn from your lecture notes, but see there are a few fitness scaling approach. So these are the option given which is not a fitness scaling approach. So one is linear scaling, B is sigma scaling, C is power scaling, and D is random scaling. So any guesses for this fitness scaling thing? Okay, Divya is telling C. Okay. Yeah, Murugesh is also telling C. Any other? Okay, so no. Actually, power law scaling is also your fitness scaling scheme. What we do in power law scaling, we multiply our fitness value by we power our fitness value by a constant k. So like if our search space is only from 0 to 5, and our fitness value is coming 125. So what we have to do to fit this 125 in this scale 0 to 5, what we have to do is we have to do 1 by 3. We have to have a power 1 by 3 of 125 to fit this 125 in our scale 0 to 5. So this power scaling is a type of fitness scaling approach. There are other fitness scaling approach. One is linear scaling. Linear scaling, what you do, you add you add some average, you find the mean of all the fitness value in your individual population, and when you got the mean, you do something f plus some constant, like let's say alpha into f bar. F bar is your mean of all the fitness value. So by doing this, what you are doing, you are scaling, you are sorry, this will be minus, this will be minus, okay. So f minus alpha f bar. So what you are doing, you are actually reducing some constant into mean value for all your fitness values to fit in a particular scale. So this is also a scaling method. And the one is sigma scaling. Sigma scaling, what you do, sigma scaling, same thing, f minus, only the thing is alpha into, here you are doing f bar, here what you will do, you will do some sigma, f minus alpha into sigma. This sigma is your standard deviation, S3. This sigma is your standard deviation. So again you are reducing something from your fitness value to fit this term into your particular scale. So these three are actually your fitness scaling approach. This random scaling is not a fitness scaling approach. So actually this is our correct answer. Sorry. Yeah, random scaling is not your fitness scaling approach. So this is actually correct answer, because here it has been told which one is not a fitness scaling approach. So option D, random scaling, is your correct answer. Okay, and this is the thing. So question number 11, what is the difference between the multi-objective evolutionary algorithm and genetic algorithm? What is the difference between these two? Option A is MOEA follows a different selection strategy compared to GA. B is MOEA follow a different reproduction operation compared to GA. C is MOEA follow a different crossover technique compared to GA. And D is there is no difference between MOEA and GA. So which is the what is the difference between MOEA and GA? This is the question. So any guesses for this question? So any guesses for this question? Okay, Murugesh is telling. Yeah, Murugesh is telling A. Any other guesses from anyone? Okay, so yeah. What happens is, see, there is no difference between MOEA and GA. This is absolutely wrong, we know, because we know that MOEA is for MOOP, MOOP, and this GA is for single optimization problem, SOP. This GA is for single optimization problem, and this MOEA is for multi-objective optimization problem. So definitely this is wrong. Now this three we have to check. So first thing is telling MOEA follow a different selection strategy. B is telling it follows a different reproduction operation, and C is telling it follows different crossover techniques. So what happens is MOEA follow the same reproduction scheme, but the difference happens in selection procedure. Why this difference happens in selection procedure? This is because we know that our single optimization problem deals with less number of data, but here this multi-objective evolution algorithm deals with many number of data, because it is optimizing more than one objective function. So for this, our fitness assignment is actually selection assignment is actually changing, because we have more number of we have different fitness different right, we have different fitness values for different objectives. So that is why we have to select a different selection procedure in place of GA. So answer A is your correct answer. So this is your correct answer. So A. So you can also see by this flowchart. See, as our GA also, this all these things are similar. Only you have to do change in this natural selection procedure. Okay, so let's move to the next question. So let us assume original parent is given 20.85, and we have to find our mutated solution. R is given 0.6, Q is given 4, and del is given 1. Del max is given 1.5. Okay, so R is given 0.6, so you have to use this formula. You have to use the second formula. So mutation of so here you can see as R is given, R is greater than or equal to 0.5. So we have to use this formula, second formula, 1 minus 2, 1 minus R, 1 by Q plus 1, to solve our problem. As R is given 0.6, that is greater than or equal to 0.5, and once we know this delta value, we can get the mutated value by this equation, that is P original. P original is also already given, and del we will calculate by this formula, and capital del, that is maximum perturbation factor, that is also given in the question. Yeah, so del you can calculate, del bar equals to 1 minus 2, 1 minus R, 1 by Q plus 1. Q is given 4, so 1 by 5 you can see. R is also given 0.6, so you can find the del bar. Del bar is coming 0.04, and when del bar is coming 0.04, yeah, so when del bar is coming 0.4, you can use this formula, PR mutated, parent original plus del bar into del max. Del max is also given 1.5, and so our answer would be 20.85 plus del bar 0.04, del max is coming 1.5. So you will be given mutated value, that is 20.91 is coming. Now you can check the option. 18.9 is not correct, 19.9 is not correct. Yeah, 20.91 is coming, so this is your correct answer. So answer is C. So any doubt in this question? Any doubt in this question?
No.
Okay, so let's move to the next question. An objective vector in MOEA is called a utopian objective vector if its component is marginally higher than ideal objective vector. Its component lies on ideal objective vector. C is its component is substantially higher or lower than ideal objective vector, and D is its component is marginally lower than ideal objective vector. So yeah, Utopian objective vector, when this concept come when we have to minimize both this objective function. So when we are minimizing this objective function, we have to minimize this also, and we have to minimize this also. so uh, Ideally, this is our search space means this are the GA points that we are getting from our optimization. So these are the points we are getting from our MOEA, that is multi objective evolution algorithm. So out of this point we know actually that if we will we will draw a line at y, as well as if we draw imaginary line parallel to x-axis with which also intersect a minimum point of your search space, we will get a point z star. This z star is known as ideal point. So ideally our objective vector should be about here, but actually we are getting this 2 point, this point we are getting, this point we are getting. So actually this the minimum imaginary line that passes parallel to y-axis, as well as minimum imaginary line that passes parallel to x-axis and intersects our search space, that point is known as ideal objective point. And the concept of utopian objective vector is that the point should be less than our ideal objective vector. So actually the answer will be component is marginally higher than objective vector. So no, this component lies on the ideal objective vector. So this is also no. This component is substantially higher or lower than ideal vector. This is actually contradicting. This is writing both higher as lower. That is also wrong. Ours should be its component is marginally lower than ideal objective vector. So this z double star you can see, that is below this ideal objective vector. So answer is D. Okay, any doubt about this? More you can read from your lecture note about this utopian objective vector, but this is the concept. Your utopian objective vector lies marginally below your ideal objective vector. This is the concept. Any doubt regarding this?
No, sir.
Okay, so let's move to the next question. The Nadir objective vector in MOEA represents the upper bound of each objective in the entire Pareto optimal set. B is the lower bound of each objective in the entire Pareto optimal set. C is the upper bound of each objective in the entire search space, and D is the lower bound of each objective in entire search space. So any guesses for this? And this theory you must have read in your lecture note about Nadir objective vector. Okay, Murugan is telling C. Any other guesses, guys? Okay, so let's talk you to this Nadir objective vector. In previous thing we have seen that in previous sorry in previous question we have seen, we are concerned with lower bound, or this lower point of your not the entire search space, but this wide circle where you are actually getting your values of GA, that is known as Pareto optimal set. So in your Pareto optimal set, the the this circle value where you are getting your GA values, these are known as Pareto optimal set, and the entire space from here to here, if you are bounding this by a rectangle, this is known as your entire search space. So earlier the ideal point was the minimum bound for your entire search space. So like your minimum minimum bound of your entire search space, there is a point called as maximum bound of your entire search space. Like previously what we have do, we have taken a line parallel to f1, which is minimum to this search space, and we have taken a line parallel to y-axis, that is minimum to this search space. But here what you have to do, in Nadir objective vector is not concerned about the entire search space. It is concerned only about this white portion. So and also Nadir objective vector, it actually talks about the upper bound of the objective vector. So how we will find the upper bound? Here you can see upper bound you can find out by a line parallel, the same line, that ideal vector line, but that will be intersecting the Pareto optimal front. So this is Z1 star max, and this is your Z2 star max, and this is your Nadir point. So answer is your A. Okay, again I am repeating, in previous question where we are dealing with ideal vector, we are concerned with the entire search space, but here we will be concerning only with this circle, that is Pareto optimal front. So here what we will do, we will find the upper bound. In previous ideal vector as well as utopian vector, we are actually concerned with the lower bound. Here we are concerned with the upper bound, but not the upper bound of your entire search space, but upper bound of your this white circle or the Pareto optimal set. So answer A is your correct answer. Okay, so let's move on to the last problem, question number 15. So I want everyone to guess this question. Which of the following is not a reason behind increased complexity while solving multi-objective optimization problem when compared to single optimization problem? So option A is optimizing each of the objectives does not necessarily give you global optimal solution. B is sometimes a multi-objective optimization problem are provided with conflicting objectives. C is a possible candidate solution may best optimize one of the objective function but perform worst for other objective function that are present in the given multi-objective optimization, and D is none of the above. So any guesses for this? Guys, any guesses for this question? Okay, so no guesses as we are not getting guess. So let's see. So here it has been asked which is not a reason behind increased complexity while solving multi-objective optimization compared to single objective optimization. So option A. Option A is optimizing each of the objective does not necessarily gives the global optimum solution. So that is exactly right, because we know that there are many function over here. Some are increasing, some are decreasing. At a point, see, this is decreasing, this is increasing. So if we are only optimizing this thing, and we at the moment we are not simultaneously optimize this thing, so we will not reach the global optimized solution. So this is actually problem. So this is right. Next is sometimes MOP are provided with conflicting interest. I have told you that here could be F1, like example as I have discussed, there could be F2, and here in the example I have told, there like minimize cost, so there can be we have to minimize this f1, and here we have to maximize the comfort. So we are putting two objective function. One we are doing the minimum operation, and then one we are concerned with maximum operation. So actually this is conflicting objective. So this is also true. C is a possible candidate solution, may not best optimize the function, but perform may best optimize for one objective function, but perform worst in other other objective function. Like if this is your graph, this is your f1, this is your f2. Same example I am taking. F2 cost we have to actually minimize, and comfort we have to actually minimize. So if your GA gives you solution like here, so here for cost this is okay, this point is very okay for cost, that is this point is very okay for f2, but this point is not okay for f1, because comfort also we required more. So comfort, this point is not okay. So this is what the C point is telling, this is also right. So we have to find actually which one of the following is not a reason behind increased complexity. So all this are reason behind complex between all these 3 points are the reason for increased complexity for your multi-objective optimization. So answer D is correct. So any doubt regarding this?
No, sir. Sir, no, sir. Sir, I have one question on question number 9.
Question number 9. Okay, let's see. Okay, this question, yeah. Yes.
Yes. Yes, sir. Suppose I am using my search space is 0 to 1, one condition.
Yes.
Another one search space is 0 to 10.
Yes.
Which one is preferable according to the GS to get the best solution?
See, you can also do from 0 to 1, you can also do from 0 to 10 also. But whenever your solution is coming in 0 to 1, it should be complete range from 0 to 1. Like some solution should have fitness of like 0.1, some should have 0.2, some should have 0.3, some should have 0.4, and like this. Not your GA solution should not be particularly concentrated to 0.5 or 0.6, not like that. It should be divided in the entire range. So that is the concept. So that is not true that if you will choose like your scale can be 0 to 1 also, your scale could be 0 to 10 also, your scale could be 0 to 100 also. So this is called scaling. So scale you can choose, but the thing is your GA solution should be on the entire range, not particularly concentrated to a point. That is the concept. Okay?
Sir, that means 0 to 1 also give the best result.
Yes.
0 to 10 also give the best result.
Yes. Perfect.
That's
not the thing.
Okay, sir. Thank you.
Is guys any other doubt apart from this? Am I audible to all of you? Okay, so I think there are no other doubt apart from this. So I am ending the session for today. So go through these slides, whatever slides I have provided you till now. All these links you will get from in that problem solving session part of your SWAYAM NPTEL portal, where you are getting all your lecture like week 1 lecture, week 2 lecture, etc. Below you will see one segment called problem solving session. There if you are clicking, all the slides are available, as well as all these videos are also available. So there you can also go through again. If any doubt, you can probably ask me in the next class also, or any time you can, or also you can comment in that YouTube also. YouTube video also you can comment also, like this is my doubt, so according to that we will discuss in the next class. Okay guys?
Okay, sir. Thank you. Thank you very much, sir. Sir, can you share your email ID, sir, so that we will get some
Yes,
clarity?
email ID. Okay, this is my email ID. If you want to mail something, you can mail. I will try to answer. Okay? So thank you all of you, and have a very happy Holi. Today also I think Holi is in some places, and tomorrow also we will be celebrating Holi in some places. So very happy Holi to all of you. Okay? So bye. Thank you all of you. Okay? Okay. Okay, so I'm terminating the session. Okay?